А если на ней звук? Хорошо. Okay, so we continue localization of modules. So remember that last time we defined operation, we start with a module, which is an R module, and we define, if we have a multiplicative subset inside R, we can define localization of the module. The general notation is S inverse of M. So this is module over the localization of the ring. And elements of this localization of the module are just fractions of the form M over S, where M is in the module M and S is in the multiplicative set S. So we can localize not only rings, we can localize also modules. We proved one general observation. Now I want to formulate the theorem, which is completely analogous to the theorem for rings that we proved last time. This is about the universal property. So universal property, but now for modules, for localization of modules. So I'm not going to prove this, but at least I want to give you a statement. You can see this more or less the same. So let N be an S inverse R module. Now consider psi a map M to the N. This is an R module or R linear map. So notice that N is given as S inverse module, but we can also consider this as an R module, right? Since we always have map to the localization, and any module over the localization of the ring is also a module over the ring, and this is essentially just an example of the restriction of scalars. So we can consider this R module map. So the statement is the following: there is unique map, so unique S inverse R module map. So let's call this rho. This is a map from the S inverse M to the N, such that the composition, rho composition with the iota, well, I'm going to say the iota S, but well, it's not completely convenient notation, because of course this map iota not just depends on the S, it also depends on the module. So the iota is just the canonical map to the localization. Now here we have map psi. This is N. And this is the map rho. So if we try to prove this, the proof will be more or less the same as for the ring, so I'm not going to prove this, but I want to, no, okay, so maybe I'll do this later. So from this theorem, we can derive essentially the same corollaries as before. So part one is that if you localize a module and you get exactly the same module, so localization doesn't do anything. This happens if and only if M is actually already S inverse R module. And property 2, so if you take a map alpha between two modules M and N, so this is module map, so R module map. So then again, there is a map which we can call localization of alpha. So this is a map Well, check this. I'm not sure about the kernel. So for any map between two R modules, we have a map between localizations, and such that we have the following commutative square. So M is mapped to the N. So then we have two canonical maps, iota. So maybe to get better notation, I also add index M and N, since this map depends on the set S and also depends on the module. So this will be a canonical maps to the localization. And then there is a map which we can call localization of the map S inverse alpha. So there is such map, so that the diagram is commutative.
Does this mean that M is an S-1 R module?
Well, it means that somehow on this module you already have the structure. Well, you can multiply elements on the fractions from this ring.
Does it mean that every element of S is invertible on N?
Yes, well, that's also true. Okay. So the proofs for theorem and for corollary is more or less the same. I just want to give you a remark. You can write an explicit formula for the localization of the map. So suppose you want to localize a map, and then you want to apply this map to the fraction, say M over S. So what's the answer? Well, the answer is quite simple. You just take alpha, apply this to the numerator, and then use the same denominator. So now we have something interesting, which is not something that we already know, some new information. So the next theorem is called sometimes localization. Localization is exact. So in the following sense, if you have a if you have an exact sequence, M prime mapped with the map alpha to the M, then there is a map beta which maps this to the M double prime. So if this is exact, of course in this case we can only talk about exactness at this position M, right? So it means exactly that the image of alpha is the same as the kernel of beta. But if we can prove this for one position, of course this follows for any other position. So this would be exactness for any any exact sequence will be but the localization will be mapped to the exact sequence. So if this is exact, so then the localization S inverse M prime, here we have S inverse alpha, S inverse M, S inverse beta, S inverse M double prime is exact. Okay, so proof. Well, first of all, first observation that if I consider the localization of the composition of alpha and beta, and just looking at this general formula for the localization of the map, we can say that this is composition of the two localized maps. So in this sense, the localization is actually a functor. So it not only acts on the object, it also acts on maps between them, and it maps compositions to compositions. Now, what we can say? First of all, we know that the composition of alpha and beta, by the exactness here, this is 0. So it means that this thing is also 0. So this composition, composition of two localized maps is 0. So from this, we can immediately conclude that image of the map S inverse alpha is contained in the kernel of the map S inverse beta. So I want to show that actually image is the same as the kernel, so we have inclusion in one direction. Now we need to show that there is inclusion in the other direction. So let's take something in the kernel. So let fraction M over S be in the kernel of the localization of the map beta. Well, what it means? It means that from this we can say, well, just by the, again, essentially by looking at the formula for the localization of the map, we can say that beta of m over s is equal to 0. Right? But this means if just now looking at the definition of how we define the equivalence relation, this means that there is an element, say t, in the multiplicative set S, such that the product of the t and beta of m is equal to 0. Well, t is an element in the ring, and beta is R linear, so we can as well say that beta of the Tm is 0. Right? So now we have exactly so this thing. So if something is in the kernel of the map beta, this is product of T and M, this has to be in the image of the alpha. So by the exactness, we can say that there is M prime in the module M prime, such that Tm looks like alpha applied to this M prime. Okay, so but this means that if I look at this fraction that I started with, m over s, so m over s, I can multiply and divide by the element t. Now this will be alpha of the m prime over ts. But this is precisely the localization S inverse alpha applied to the fraction m prime over ts. So where m prime over ts lives in the localization of the m prime. And that's the end of the proof. Okay, now let's derive one simple observation, but which is quite important nevertheless. The observation is the following. So let's take a prime ideal in the ring R. So in fact we can associate with this prime ideal a field, and actually we can do this in two ways. Well, first of all, I can take the quotient. So this is a domain, and for any domain I can construct a field just by applying the construction Q to this domain. So this is a field, and a field that depends on this prime ideal. But I can also do another thing. I can localize my ring at the prime ideal P. That's a local ring. It has unique maximal ideal. So the unique maximal ideal is PRP, which is, as we know, this is exactly the localization of this prime ideal. So the question is, are these two fields the same? Well, indeed they are actually isomorphic. And notation is that in this situation we denote sometimes k of p, sometimes p. I think people also write k and p as an index. It has nothing to do with the localization, just a notation for this thing. So maybe I prefer this k depending on the p. And this is by definition this thing. This is called the residue field. And the residue field at prime ideal p. Okay. Okay, so The proof, of course, follows immediately by the exactness of the localization. So essentially, we look at the short exact sequence for this prime ideal P, and then we localize the short exact sequence. So localize at the prime ideal P. So when we localize prime ideal P at the prime ideal P, what we'll get is PRP. Now here we have the localization of the ring, and here we have, well, we need to do the localization, so let me just write for a moment, this is S inverse of this thing. So this this exact sequence, so this short sequence is exact. But now, well, this is almost because of the theorem.
Yeah, but we prove that it's exact in the middle. But we didn't prove that it's exact.
Well, this is exact in the middle for any. You can imagine that you have any continuation of the sequence to the left and to the right, and if you consider any term, exactly the same argument would work. So if you can show that this is, if you start with this exact at this position, after localization is exact at the same position, it will be exact at any other position with the same proof. So that's what I mentioned during the proof. So localization is exact in all possible ways. You can take any exact sequence, localization maps this to the exact sequence of any length. So in particular, this is true for short exact sequences. Okay, so we're done if you know how to show that this is true. And do we know that this is true?
Depending on what S we have.
So S in this case, of course, is just complement to the prime ideal. This all the localization of the prime ideal, so by definition, this localization is the complement of prime ideal. But if you look just at the definition, what we're doing here, so here you're supposed to take in the quotient ring for all non-zero elements and consider them as the fractions. And here, what you do essentially the same thing. You consider this quotient, and then you consider as denominators everything which is not in the prime ideal P. So fractions here and here are exactly the same. So that's at the end of the proof. Okay, so next theorem, which might be the most non-trivial observation about the localization of modules. So we have the isomorphism of following form. If you take the product of the localization of the ring,
It's like the